Welcome to the podcast on analyzing functions by graphing and using zoom and trace features. That's what we'll be doing in this. We'll be doing a lot of zooming and tracing. We'll be analyzing graphs to answer questions about functions. And in the first example, we'll also get a chance to look at the topic of x and y intercepts and maximums and minimums. So let's just get started. Problem 1 says the height in feet of a projectile fired from the ground is given by h of t equals 20 plus 3000 t minus 16t squared. So in this equation, h of t, remember that's just another fancy name for y. Y, or h of t, is the height in feet of the projectile. And so t you expect to be the time, and it says where t is the time in seconds after the projectile is launched. So if you were to put in a t equal 5 here, that would give you the height of the projectile 5 seconds after the projectile was launched. So how high is the object 10 seconds after launch? What is the maximum height reached? When is that maximum height reached? So that would be in terms of how many seconds after launch. How long is the projectile above 105,000 feet? And how long is the projectile in the air? Well, it's in the air till it comes back down and hits the ground. So let's see how we would use this function to answer these questions. Now, the first thing you note is that it's in terms of h and t. And what go into our calculator is y and x. So I'm going to just rewrite the function right above the problem here. And instead of h of t, I'm just going to say y. And you notice the calculator continues to disappear. Every time I touch the screen, it disappears. I don't know what causes that, but it's just something we'll have to live with. And we can't use a t either in our graphing portion of our calculator, so I'm going to change t to x. So that'll be minus 16x squared. So whenever I'm referring to the height, I'm going to look at y. Whenever I'm referring to time, I'm going to look at x. Okay, let's bring the calculator up and enter the function in the calculator. I've already taken it. If you were back on your main screen, you'd be here, maybe have some problem here like this, and you'd be wanting to enter a function. You notice all your keys for graphing, zooming, window keys, setting up table of values, all those keys are up here in this little row that's right beside the screen. So to put in your y, just hit the y equal key. Now you'll notice I've put some in. Those are for later examples, and I just put those in there to save time. But let's go ahead and enter this one. So it's y equals 20 plus 3000 x minus 16 x squared. And we've got the basic function loaded in the calculator. There's nothing to delete from a previous function. Now the next thing to do is to set a window. And at this point, we don't know how long this flight is. We don't know how high this is. So right now, we virtually have no way of telling how we should set our x and y windows. So what we're going to do is a little experiment. We've already loaded the function. Let's just do a little test on a table of values. If a projectile is going to get over 100,000 feet, it's certainly going to be in the air for a minute or two, I would think. So when we set up our table, we'll go second table setup to generate a table of values. And yeah, that's not bad. Table minimum 30 seconds. Well, maybe table minimum 0. And then delta table 30, that would mean every 30 seconds we'll get a look and see how high it is. Now why don't I do like 1 second? Well, nothing's going to go up 100,000 feet and come back in 1 or 2 seconds. This is going to take some time, so I'm going to use a delta table of 30 seconds, but that may be so crude that we end up without a very good window, but let's just give it a try. I'll hit second graph to see my table. Let's see what kind of information we get. Well, if you look down here at 90 seconds, looks like it reaches a height of about 140,000. If you look at the two numbers each side of that, they're almost equal. So if you imagine a parabolic arc, that's going to say that the maximum altitude is going to be somewhere around 140,000 feet, maybe 150, maybe 160. Also, it reaches its maximum at 90 seconds, so I think it'd be back to the ground in about 180, but it's not. You can see that here at 180 seconds, it has not made it back to the ground. It's still 21,000 feet high. So I'm going to use about 200 seconds. I'm going to take my x-axis from about -20 to about 200, and I'm going to take my y-axis. So let me just make a note of that. X, -20 to 200. And y, we said it got to about 140,000 feet, so I'm going to go about -20,000 to about 160,000. So let's bring the calculator back up. Sorry it keeps disappearing on us, and hit the window key. Now to set the window, we wanted our time to go from -20 seconds to 200 seconds. And the reason I make time -20 is because I don't want my y-axis to be right along this edge. I'd rather move it over a little bit so I can clearly see the y-axis. So that's why I use -20 on the time. So I'm going to arrow down, put in -20 for my x-min. I'm going to run this experiment for 200 seconds, so I put 200. Whoops, got 2,000 there. Got to be careful about that. And then I want to mark my graph about every 20 seconds. So I don't get too many marks there. That'll put about 10 or 11 marks on it. Whoops, I said 10, I meant 20. And now for the height, we said the height was going to go from -20. Now that's -20,000, not -20, to 160,000, not to 160. So I come down here and I go -20,000 to 160,000, 160, 000, enter, and then how often to mark it? About every 20,000. Again, that's going to put, 8 marks, 9 marks on the graph, so I'll mark it every 20,000 feet of altitude, 20,000. And now we're ready to graph it, so I hit graph. And let me make a comment about that arc. That is not the flight arc of the projectile. This upper distance is the height, because the y-axis does represent the height. But the x-axis does not represent the distance from the launch point. So you are not seeing here the flight of the object. What you're seeing is a graph of only the height of the object versus the time it's been in the air. The x-axis is a time axis. And whatever the time is out to this point here, that is going to be our total time of flight, because that's when it hits the ground. It doesn't keep burrowing under the ground when it gets to the ground. When it hits the ground, it crashes and stops right there. So let's go ahead and start answering the questions. And the first question says, how high is it after 10 seconds? So what I want to do is I want to use the trace feature. Now, you don't have to do this on your calculator, but I've found through sad experience that I do have to do it on this one. I have to go to a higher order graph to get the trace to work correctly. Yeah, it won't graph on F1. I have to go to, well, there it goes, function 1, and it is graphing, or it is tracing. I had to go through a little more trouble. All you'll have to do with your calculator is hit the trace key. So now we're up there tracing. We're in about the middle of the graph at x equals 90 seconds, and we want to know how high was it at 10 seconds, and 10 seconds would be back in here somewhere. Because remember, I think we marked off each mark on the x-axis was 20 seconds. So 10 seconds would be about halfway between here and 0. And I'm not sure what that smudge is there. Been having a little trouble with the calculator, which has held me back some. Let's get x down to 10 seconds there. X is 15 seconds. 5 seconds, that's a little too far. 8 seconds. 10.4, that's pretty close to 10. We could do a little bit better than that. We could zoom it and box it to get closer to 10 seconds. So since that's kind of low, let's make a guess though. You can see at 10.4 seconds it's 29,000 or almost 30,000 feet. At 8 seconds it's about 23,000 feet. So in that 2.5 seconds it went about 7,000 feet. So in about 2 of those seconds, I'd expect it to go maybe 5,000 feet. So I'm going to think, let's see, from the 23 that it went about 28,000. But let's go ahead and do a little zoom in box. Now if we want to get a closer look at this, we can do what's called a zoom box. So I'm going to hit the zoom button, and then the very first thing is the box button. And I want to draw a box right around this point here. So the boxes are drawn from the left to the right and to the right and down. So I would like to start my box over here about where this mark is at the second mark on the y-axis. That would be a good place to start that box, and then put that area that I want to look at in a box. So to get it there, I arrow up and I arrow to the left to get me a starting point. Now when I hit enter, this shape of a little plus sign is going to change to a box sign. So now you can see it's more in the shape of a box, and now to put the point of interest in the box, I bring the box to the right and down. And when I hit enter, that part of the graph will blow up and fill the screen. And now we'll be able to get closer to 10 seconds. You can see that right now we're at 10.4. Again, a little bit of trouble trying to get the tracer to come up. There we go. And I want to go down to 10 seconds. This time I'll be able to get a whole lot closer. There's 9.97 seconds. We thought the height would be about 28,000 feet. It's more like 28,360. I'm going to say 28,400 feet. So for the first answer, how high was it in 10 seconds? In 10 seconds, it was 28,400. The second question asks, what is the maximum height reached? Well, to do that, we have to go back and view the original graph again. So that means we need to go back to the original window. I don't know if you can put that in with a second enter, but I'm going to try. No, that doesn't work. So we'll have to put our window back in. Our window went from -20 to 200 with a step size of 20, and then it went from -20,000 to 160,000, again with a step size of 20,000, so that would do it. Put in the graph. And you can see a couple of things here. Number one, the power of x is 2. And since the number of turns has to be no more than 1 less than the power of x, this one turn is the only turn there is. So this function's never going to get higher than it is right here. So to see what that height is, again, I'm going to do a trace. I just keep trying until my tracer appears. There we go. And right there the height is 138,000 feet. Let's arrow over a little bit to get more in the center there. There we reach the height of 140,600. If I go to the left, it gets a little smaller. It was 631, now it's 613. If I go to the right, now it drops way off. So this is fairly close to the maximum height. I'm just going to call it 141,000. So max height, 141,000 feet. When is that height reached? Well, we're just going to go ahead and use this. It looks like it reached the max height. It looks like this is a hair past the max height. So I'm going to say at 94.5 seconds just to make it roughly. So I'll just say here at 94.5 seconds. And that could be off a hair, but that's close enough for what we're doing. And it says, how long was it above 105,000 feet? Well, now that would take some serious tracing. If I trace back this way, and we're looking at the height, and we want to know when we go below 105,000 feet. So there's 116,000, there's 106,000, and there's 103,000. So it jumps all the way from 103 to 107. So 105 would be right about in the middle of those. This height, 107, is at almost 48 seconds. This height of 103 is at about 45.5 seconds. So that's about 2.5 seconds differential. So if you went halfway in between those, that would be about 1.25 seconds. Of course, the best way to do this is the zoom in box and then really narrow it down to 103. But I don't want the podcast to take too long, so I don't want to do a lot of zooming and boxing. So I'm just going to estimate it. About 1.25 seconds added to this would be, let's say, 46 3/4 seconds, so about 46.8 seconds. Now, to really do it, you need to zoom in box to see if that's actually 46.8 seconds. And you might want to try that on your own calculator. Let's go see the other time when we were below 105. We just keep tracing over there. Now we're at 110, 107, and down to 104. And that is between 141.5 and 139. So again, it's about 2.5 seconds. So I'm going to add about 1.25 seconds to the 139. I'll call it 140.5. So from about 46.8 to 140.5, we were above 100,000 feet. Now, how many seconds is that? Because the question is, how long was it above 105,000 feet? So what you'd have to do is subtract those two. So let's subtract those two. We'll go back to our main screen, second quit. We'll do 140.5 minus 46.8. And of course, 46.8 would be done better if you zoomed it and boxed it. And we get about 93 seconds. So I'm going to say approximately 94 seconds we were above 100,000 feet. Now, let me show you a fast way to do that one, because this is another important feature of the calculator that you get to use once in a while. It's called second trace 5. I'll write it up here just so you'll kind of have a note. You can put it in your notes. Second trace 5. Second trace 5 lets you identify a point of intersection of two curves. So I want to know how long was it above 105,000 feet. So let me go back to my functions and set in a second function. Y equals, what do you know, 105,000. Now that's going to be a horizontal line cutting across the graph 105,000 feet high. So let's see how close our guessed answer was by getting a really exact answer. Notice that both the first two functions are highlighted, so they're both going to be graphed. So I hit graph. Here goes the original trajectory. Here's the line at 105,000 feet. Now to determine exactly the time at which it crossed 100,000 feet, here's what you do. Bring up your tracer. Doesn't matter which one of the functions it's on. Put it on either one. Get it close to one of the points of intersection that you want to know what the value is, and hit second trace 5. So here's second trace, and that brings up a menu under calculate that says calculate the intersect for 5, and that's what we want. Where did they intersect? So we hit 5 and it says, well, what's the first curve you want to look at? Well, the one that we're on, so just hit enter. What's the second curve you want to look at? Well, when we hit enter the first time, it jumped to the other curve. You couldn't see it because it looks like it's on both curves, but it did jump to the other curve. So just hit enter again. And now hit enter again. This word here, guess, what that means is get your cursor close to the point of intersection. Well, our cursor is almost sitting on the point of intersection, so we don't have to move it at all. I hit enter. And it gives me the point of intersection, which it says was at 141 seconds. So we had said 140.5. It was actually 141. Let's go back and look at the other point of intersection. I'll arrow back to the other function. or to the other point of intersection. You want to do this under a trace though, so let me hit the trace key. Again, these troubles I'm having with trace you will not have. Don't worry about it. When you hit your trace key, it'll trace. So again, I'm close to the point of intersection, so I'm going to do a second trace 5. It says first curve. I'll use that for my first curve. Now you can see that it did jump to the lower curve for the second curve. That's my second curve. I want to know where those two curves intersect. So it says, give me a guess, get close to where they intersect. I am close. So basically you're just hitting enter, enter, enter. And it gives me an exact point of intersection at 46.5. We had guessed 46.8. So let's see how our rough guess method compared to a more accurate method for determining the time above 105,000 feet. So this time we'll do 141 minus 46.5, and we get 94.5. So it looks like our rough guess method was off by roughly a half a second. So our rough guess was okay, but this is a better answer. And then the last time it says, how long is it in the air? So what we need to know is, what is the time when it hits 0? So let's go back to the graph. It's still in the air. Let's trace it. And let's see at what time. Now remember, time is x. So right here it's been in the air 111 seconds. How long until it hits the ground? And we'll just do a rough one again. Boom, though, that's pretty close to the ground, and that's about 186 seconds. 186 seconds, time of flight. Didn't spell flight very well. Time of flight, carefully. 186 seconds. This was time above 105,000 feet. And we finished the first problem. Okay? The second problem also is kind of space oriented. It says the weight, it should say in pounds, and I left off the pounds here. So I'm just going to put a little arrow there after the N. The weight in pounds, the symbol for pounds is LB. The weight in pounds of an astronaut X miles above the Earth is given by weight equals 175 times 4,000 over 4,000 plus X squared. Now, this 4,000 over 4,000x, this is a rough approximation of the radius of the Earth. And so what we're saying is at sea level, when x is 0, it's just 4,000 over 4,000, which is 1. So what we're doing is we're talking about an astronaut who weighs 175 pounds at sea level. Okay, and it says at what altitude will he weigh 150 pounds? Now, as you get further from the Earth, the force of gravity gets less and less. So after he gets so many hundreds or so many thousands of miles from the Earth, his weight will drop. He'll no longer weigh 175. He'll only weigh 150. His mass won't change. The total content of his body won't change. But the force with which gravity pulls on his body will change. Then how high would he have to get to weigh 99 pounds? And what will he weigh at a height of 10,000 miles? So again, we can do this all by just putting in the function and tracing it. So to put in the function, you go to y equals, and you notice that I already put it in. 175 times 4,000 over, and since there was more than one number in the denominator, I put the denominator 4,000 plus x in a bracket and squared it. And you could put a bracket around all that, but it's just not necessary. Now I don't want to graph the first two functions, so I'm going to go disable them, move my cursor left, hit enter. Bring my cursor down to the next function, hit enter, and both those are no longer visible to the calculator. Now I want this one to be visible, so I bring my cursor down and hit enter. And now my calculator can see this highlighted function, which is the one we're working on. Now the next question is, what do we use for our x and y's in our window? Well, y is going to be weight, so we're not going to be using a w, we're going to be using a y here. And the weight will have to go up to 175 pounds, but it won't have to go any higher, because as you move away from the earth, you'll get lighter and lighter, not heavier and heavier. On the other hand, the x, I don't know how far this is going to take to meet all the conditions of the problem, but I know for one thing I have to go out to 10,000 miles, so I at least want x to go to 10,000 miles. So here's the way I'm going to set it up. And I may have to change this once I get a look at the problem. But I'm going to start off x from negative 1,000. Again, just to move the y-axis over, that's all. The only reason I do that, to 10,000. And I'll put a mark on it every 1,000. So every time you see a mark on the x-axis, that's 1,000 miles. The y, I know, has to go up to 175. So I'll just, and I don't want the y to lay down on the bottom because I need to be able to see my trace numbers. So I don't want to start y at 0. I'll start y at 20 pounds, see if that gives me enough room, and go to 170. If it doesn't give me enough room for my trace numbers, then I'll increase that 20 pounds. And I'll put a mark on this one every 20 pounds. Whoops, wrong spot. There we go. Mark every 20 pounds and we'll graph. Well, that's not a very informative graph. Let's go back and take a look-see. 175 times 4,000 over 4,000 plus x. Let's look at our window. X, our distance from the earth, goes from negative 1,000 to 10,000. So at 4,000, we should be at a weight or at 0, we should be at a weight of 170 pounds. So why is that not happening? Let's see, y min needs to go from negative 20 to 170. Let's see if that does anything. No, that's still not happening. We're not getting the graph of that function. Okay, here's the problem right here. I meant to bracket the bottom two numbers. If so, then I'm going to have close bracket squared. When I look at my function in the calculator, all I have is a closed bracket squared. I'm missing a closed bracket. So I need to add in a closed bracket there before the squared. Another closed bracket squared. Okay, that should correct the problem. Now I hit the graph, and there we go. Okay, first question says, at what altitude will he weigh 150 pounds? Now remember, the altitude is x, his weight is y. So I'm going to hit the tracer. Again, I got to get it activated. You don't have to do this. Yours will come up immediately. And I want him to weigh 150 pounds, and right now it says he only weighs 38.7 pounds. So we're way too high. Okay, now he's 98 pounds. That's still a long way from 150. There's 152. That's pretty close to 150. At that point, he's only 287 miles high. And if I click over just one more, he drops all the way down to 144. So that's not a very good look. So this would be a good time for a zoom-in box to get a good altitude for him to be 150 pounds. Now notice the graph is going pretty vertically here, pretty much up and down. So if you want to zoom in box here, make a box that also goes pretty much up and down. So I'm going to hit a zoom box, and I want a vertical box, so I'm going to go up quite a few notches. I'll go up 4 clicks. I'm going to go up 5 clicks. Then I'll go to the left a couple of clicks. And now I'm ready to draw my box, so I hit enter. And my little cursor changes to the shape of a box. It's kind of hard to see here, but it is the shape of a box. Then I'll go right about 4 or 5 clicks. And I'll come down. Let's see, I think I went up 4 clicks. So I'll come down about 8 clicks. I'm not sure if I'm picking up every click, though. It's kind of hard to tell. Punching on this computer screen exactly what's happening. Now to look in there, I'll hit enter, and this time I should be able to get his weight much closer to 150 pounds. So I'll hit trace. Got an arrow till I see my tracer. There's my tracer. He's listed as a weight now of 155 pounds, so I start working that down. Now notice how much closer I'm going to be able to get to 150 pounds here. This is going to be really close. Yeah, there's 150.1 pounds, so that's close enough. That's at an altitude of 319 miles, almost 320, so I'll call it 320 miles. Now, how high would he have to be for that weight to drop all the way to 90 pounds? Well, let's go back and restore our original window. In our X, we went from negative 1,000 to 10,000. We marked it every 1,000. And on our Y, his weight, we went from negative 20 to 175. And we marked it every 20 pounds. And graphed it. So here comes the graph, and now we want to know how high would he have to be to weigh 99 pounds. This time we won't zoom it and box it. If we can't get close enough, we'll just guess. There we go. There's our tracer. Right now his weight is 38 pounds. We need it to be 90. Now if you stop and check here, here's his weight is 83 pounds, so we're getting close. 90.1. Well, that's real close, so this should be a pretty good thing. At a height of 1,575 miles, he weighs 90 pounds. So for 90, whoops, well, 90 is 99. We need to get him up to 99. That took him way past 100. Let's see. There's 98, and that's at about 1240, so he'd have to go a little shorter than that. So I'm going to say 13, maybe 30. I'm going to just use 1340. 98.17 is close enough to 99. I'll say 1,340 miles. So for 99 pounds, 1,340 miles. Probably more like 1,330, but that's okay. And then what will he weigh at a height of 10,000 miles? Well, I think our axis only went to 10,000. So this is going to be a tougher one to do. Let's start arrowing over till we get to 10,000 miles here. Now, one thing you could do is you could just do that through your table. I'll show you that in just a second. But we'll arrow over to 10,000 miles. Now, right here we're 8,000 miles high, 9,000 miles high, and bingo, there's 10,000 miles. What does he weigh? He weighs 14.28 pounds. Wow. What a diet, huh? Let's see how we could have got there with our table. If I went to do a table setup, I'd go second table setup. And if all I wanted to know was his weight when X was 10,000, I could just start the table at 0 and make the delta table 10,000. And then when I went to look up my table, right here at 10,000 miles, he weighed 14 pounds. So we could have done it that way as well. But since the graph was always there, it wasn't too hard to just trace it out. Okay, I have one more sample problem. Let's take a look at it. It's on another page. And it's one that you'll definitely want to be familiar with. It says the cost of removing X% of the pollution at an industrial plant is 200X over 4.65 minus the cube root of X. and X is in a percent. Now what that means, it says if 10% is removed, X is 10. A lot of times when you get a percent problem, you change that to a decimal when you plug it in. But this problem says X is the percent. So if you're removing 10%, don't put X as 0.10, put X as 10 in there. And it says, what is the cost of removing 50% of the pollution? So let's go ahead and set that up. Again, as a time saver, I already have that function located. It's down here, my last function. I don't want my third function to be seen anymore, so I'll hit enter on that one. Come down to the next one, hit enter on that one. So now we can see that fourth function. Looks like it's entered correctly. Yep, that is correct. So we need to get a window. Well, it's going to be pretty easy on the X because X is the percent that you remove. You can remove 0%, then you haven't removed anything, or you could remove 100% and then there is no more pollution. So X has to be from 0 to 100. But again, so that I can see the y-axis and it's not running along the edge, I'm going to start my X at -10. And then I'll take it out to 100%. And I'll mark it every 10. Whoops, I didn't do -10, I did -1. I wanted to do -10. And I'll mark it every 10 units. That'll give me about 11 marks on the graph. That's not too many marks. Now, what are these costs going to be? Well, it says how much can be removed for 100,000. So I know I want my cost to go to 100,000. How much can be removed for 3 million? How much does it cost to remove 75%? Oh no, that's not 3 million, that's just 300,000. I guess we could set our window initially to go from like -30,000 to 300,000. So let's try that. I'll arrow down. The minimum, -30,000 to 300,000. And we'll mark it every 30,000 so that we don't get too many marks on the graph. That looks good, and we'll graph it. Well, we don't get much information early in the graph. Boy, that's really close. So I think our y-axis we've set too high. So I'm going to go back and change that. I'm not going to go to 300,000 initially. I'll go from -10,000. And we have to get up to, on the cost, at least 100,000. So I'll go to 120,000. And we'll save that big number for last. And we'll mark the graph every 20,000. Now we'll graph it. And maybe we'll get a better graph this time. Yeah, the graph shows up much earlier this time. So this will make for better traces. Okay, we need to trace it, so I'll hit the tracer. There we go. And right now we're removing 45%, and it's costing us $8,233. Remember, C, the cost, is Y. And the percent removed, well, it's already X. I don't have to change that. Only had to change the C. So what we're saying over here, Y is the cost. Y is $8,000 to remove 45%. So not much more, I would think, to remove 50%. We'll trace it out. There's 47%. And there's 48.5, 49.7. That's almost 50%. It's about 10,000. Looks like maybe 10,500. So for 50%, about $10,500. We've removed 50% of the pollution. The next question is how much to remove 75%. So let's just keep arrowing over. There's 62.5%, 68%, 74.2, 75.4. So right between these two numbers. The lower of the numbers is 33,000. The higher of the numbers is 35,000, so I'll say 34,000. So 75% cost us roughly 34,000. Now look at that. The first 50% only cost us 10,000 to remove, but the second 25% cost us almost 25,000 to remove, 2.5 times as much. So now it says, well, what if you went out and you spent 100,000? How much could you remove? So let's check that out. Now 100,000 is cost, that's dollars, so that's going to be our Y. So now we want to trace out until Y becomes $100,000. So there you go, Y is $66,000. Y is $100,000, almost on the money. That's less than 101,000, and that's way below. So that's pretty lucky. I would not zoom in box here. I would say that it would, to reduce to spend $100,000, we could get rid of about 89.4%. I'll just bring that up again so you can take a look at that. Here's the money spent, and there's the amount of pollution removed. That's pretty close to 90. Perfect answer, you'd want to zoom in box. Now it says, well, how much could you remove for 300,000? We're not going to get to 300,000 this way. We need to change the window. So I'm going to modify the window to now allow Y to go up to 300,000. And I'll start it at negative 30,000 like I was going to do before. And I'll do a mark every 30,000 as well. And that shouldn't give us too many marks. We hit the graph. And this time we're not going to see anything down here because this top number is such a huge number now. So 300,000 is going to be all the way at the right extreme of the graph. But let's go ahead and get started with a trace. There's our tracer right there. See there, right there, you're spending 200,000. Or no, that's 20,000. There's 30,000. There's 60,000. And now you're removing 96% of the pollution, and it's costing you $300,000. And that's pretty close to 300,000. So I would say 96.4%. Now, is that a good way to spend money? You spend another $200,000 to get rid of about 7% of the pollution. I don't know whether that's a good way to spend money or not, but that is the answer to the problem, and that completes the podcast.